So good afternoon, everyone. We have a few more people coming in. Just feel free to get seats. Good afternoon, everyone, and welcome to 19 Washington Square North, which is the intellectual home and center of NYU Abu Dhabi here in New York. My name is Michael Puruganan. I am a professor of biology here at NYU New York, and I also run a laboratory at NYU Abu Dhabi, and I serve as the academic director of 19 Washington Square North. So welcome again. So over the course of the year, 19 hosts many different events, public lectures, workshops, conferences. It really serves as a place where people from the public and the general NYU New York community can come and learn about many different things, many different advances in science, technology, culture, and the arts. It also serves as a meeting place where people from different disciplines and also people from both NYU New York and NYU Abu Dhabi can meet. Many of the activities that is organized here at NYU, at 19 Washington Square North is organized by Sharon Hakakian-Bergman, who's the Director of Academic and Research Programs at the NYU Abu Dhabi Institute, here at the corner over there, greeting people. And she and her staff organizes many of the activities here, like the activity we're having today. So today we're very, very pleased to see all of you at this public lecture on the intriguing title, The Effective Irrationality of Science, by Professor Michael Strevens of the Philosophy Department. This lecture comes out of his work detailed in his well-received book a few years back entitled The Knowledge Machine, which was one of my COVID readings during lockdown, actually. Michael Strevens was born and raised in New Zealand and moved to the US to get his PhD in Rutgers University. He currently teaches the philosophy of science here at NYU. And his academic work is principally concerned with the nature of science, and he also applies contemporary research in cognitive psychology to explain aspects of both philosophical and scientific thinking. Among his honors, he was a Guggenheim Fellow several years back. So again, it's a pleasure to welcome you all here this afternoon for this event and this public lecture, and let me introduce Professor Strevens today.
Let me just plug in here. Well, it's really nice to be here, and I give a lot of talks, but it's especially nice to be able to give a talk right here at NYU, at my home institution, and tell you a little bit about some of the thinking I've been doing over the last, I guess, 10 years now about the nature of science. I'm a philosopher of science, so this is my bailiwick. But as Michael said, I finally put some of these ideas into print, actually in this general audience book, as opposed to just a mere academic paper. You can see from my title that there's a certain tension or even a paradox in what I want to talk about today. On the one hand, science, highly effective. Obviously, I'm going to say something good about science. On the other hand, irrationality, especially coming from a philosopher, sounds like it could potentially be a critique. Well, actually, my intention is not to critique science exactly, but to put it in a different light, to explain something about its effectiveness by pointing to features which are, on the one hand, I think, actually very well known, especially to scientists themselves, but often not understood to be quite the things that they are. Well, okay, with that very abstract formulation, I will get going. Let's begin with these two individuals who I'm sure you'll recognize some of. There's Einstein on the right, and on the left, at least, best shot at a likeness of Aristotle. Aristotle and Einstein have a lot in common, not just that wise-looking 5,000-yard stare. They are, of course, responsible for some extremely creative ideas about the way the world works, presented in a very systematic format. In Einstein's case, a complex mathematical theory, in Aristotle's case, not mathematical, but still very, perhaps if anything, even more interconnected. Both of these systems are in their own way extremely logical. The parts are tightly knit together. And both are responsive to and attempting to make sense of a lot of observable phenomena. And in particular, are responsive to any kind of empirical critique. In fact, Aristotle saying something that could just as easily be uttered in one of those classes that in American high schools they teach you on the scientific method. We should only take theories seriously if they fit with the observable evidence. So, so there's a lot that Einsteinian science and Aristotelian ancient Greek science, in fact, have in common. And in fact, if you take a few steps back and look at the people through history trying to understand how the world works, you find it's not just Aristotle. There are a number of, a long and extremely distinguished list of very serious thinkers who, in their attempts to make sense of the world, show those same virtues: creativity, systematicity, logic, and a genuine sensitivity to the phenomena, to getting the phenomena right. And here's just a selection from around the world, from the Islamic Golden Age, from South Asia, from China, and from the medieval tradition in Western Europe. Nevertheless, the traditional story we're told about science is that modern science doesn't really, that distinctive enterprise called modern science doesn't really get going until about, well, 2,000 years after Aristotle lived. What's being pointed to here is that episode that we call with capital letters the scientific revolution. Here are some of the characteristic figures of the revolution, and as you can see, it's the 17th century, where many historians of science, many philosophers of science think science really gets going. And I think there is, in spite of everything I've said up until this moment, there is something right about that. There is something really distinctive about the enterprise that begins at or around the time that these thinkers are doing their work. I want to start by just giving you a little bit of a sense of what I'm pointing to when I say there's something distinctive in this way. I'll do it with the help of an example. So back in antiquity, in the time of the ancient Greeks and Romans, there are a number of different interesting ideas about the structure of what we now call the solar system. There was, of course, the geocentric system, to which Aristotle himself subscribed, that put the Earth at the center and had the sun and the moon and the planets revolving around the Earth. But that was by no means the only idea that was taken seriously at that time. As I expect many of you know, the Greek thinker Aristarchus of Samos, just really less than 100 years after Aristotle, suggested this system with what's going on here. The sun at the center, and the planets going around the sun, and the moon going around the Earth. Something seems right about that. And so Aristarchus' ideas were widely known, and there they were sitting alongside Aristotle's, and there were more. Later on, a system that became especially popular is this one. Here we have the Earth at the center again. The sun is going around the Earth, but the planets, the inner planets, Mercury and Venus, are actually going around the sun. And then there are other variants as well. So here is a whole set of interesting and inspired stories about how the sun and the planets and the Earth are all moving with respect to one another, that persisted for those thousands of years until the scientific revolution. And then we see something happen. We see suddenly, from these different systems, one is selected and deemed to be the right one. Well, it is the right one. The heliocentric system with the sun at the middle. So this I take to be distinctive of the kind of achievement that modern science really distinguishes itself in virtue of. The ability not just to conjecture very interesting, very systematic stories about the way the world works that fit pretty well with what we see up there, but the ability to then winnow those stories and pick out just one, which is the one. Likewise, just reading that list of names there, something like with respect to, say, stories about the physics of the world, there have been many theories over many thousands of years coming from all parts of the world, but it's with the scientific revolution that one theory begins to rise above the rest. the crowning glory here is Newton's theory of gravity. Now, we now know that Newton's theory is not correct, so it's not as if science always just zeroes in on exactly the right story, but it does zero in on a story, and typically a story that then becomes an important building block for whatever comes next. So there's a certain sense in which modern science is a progressive or cumulative enterprise in the way that the ancient sciences, the sciences of places like China and India and the Islamic world were not. That has to come with a bit of an asterisk when I say progressive or cumulative. There are many, of course, there are many blind alleys, there are many points at which you have to go backwards to make progress rather than forwards, but still overall. This is the kind of achievement that I see as distinctive of modern science. And here I think I'm just echoing the many, many thinkers who have seen something important happening in or around the time of the scientific revolution. So the question I want to now talk about is this question, which has been around for, of course, for as long as modern science has been around, certainly for as long as people have been distinguishing the scientific revolution as a special time in the history of thought, of human thought. Again, I'll attack this question by looking at a particular example, and here's Einstein again. This time, though, he's paired with a different character. That's Arthur Eddington, his contemporary. Eddington was one of the very first champions of Einstein's new theory of gravity, Einstein's general theory of relativity, which after over 200 years of Newtonian supremacy overthrew that reigning theory and replaced it with something new. Einstein first published the final version of his theory in 1915, 1916, right in the middle of the First World War, which of course Eddington, who was English, was arrayed on the opposite side of Einstein in some sense during that war. But Eddington immediately saw the virtues of Einstein's theory and became a great advocate for the theory. He was able to do this because he was, in fact, himself a very talented mathematician, a very talented mathematical physicist. Einstein's mathematics, as you may know, is very complex and, in fact, esoteric. What Eddington, when we can imagine Eddington contemplating this theory, he had some inklings of it from Einstein's earlier versions, but seeing the final version as it was presented in, as I say, about 1915, 1916, and thinking to himself, this is not a quote from Eddington himself, but it's certainly a view we knew he had something in the ballpark of, that here is a really beautiful theory. It achieves, I won't go into the details about special relativity and so on, and some of you will know this stuff back to front or have some inkling, and others will probably want me to move on without mentioning differential geometry at all. But Eddington saw the elegance of Einstein's new theory at a point where really it hadn't been yet in any way subject to the kinds of tests that would ultimately convince scientists that Einstein was right and Newton was wrong. But Eddington was nevertheless convinced because of the elegance of the theory, because of its mathematical beauty, and he certainly wasn't alone in thinking that beauty was a sign of truth in some sense. Of course, not an infallible sign of truth. We have many beautiful but false theories, but a kind of a sign that a physicist theorizing is on the right track. So here are a few testaments to the probative power of beauty from some other famous physicists. Murray Gell-Mann there saying, beauty is a chief criterion for the selection of a correct hypothesis. Paul Dirac saying, it's more important to have a beautiful theory than to have your equations actually fit the world, at least temporarily. Dirac did think in the end, if you were on the right track, you would end up with a theory that would not run full tilt into the observable facts. And Steven Weinberg, we wouldn't accept any theory unless it were beautiful. So these are some pretty powerful statements, maybe slightly exaggerated, but still to be taken very seriously. Now moving away from a battery of Nobel Prize winners, here's Brian Greene, the physicist, telling us about just the ordinary non-Nobel Prize winning kinds of physicists. Also, like Eddington, taking beauty to be a mark of truth, using it not as a final, sort of a property on which we can make a final determination, but an important sign that something good is happening. However, in his book, The Elegant Universe, Greene goes on to remark that these judgments about beauty, however helpful they may be to individual scientists in deciding what ideas to develop, simply, in some sense, do not count. As he puts it, they do not arbitrate scientific discourse. The only thing that matters is hard experimental facts. And Eddington knew this, felt this doctrine very much in his own bones. And so he knew if he was going to convince the rest of the world that Einstein was right, it was not enough to draw on his own expertise and his great skills also, I should say, as an expositor. He was really one of the great physics popularizers of the early 20th century. It was not enough to draw on his mathematical skills or his rhetorical skills. He had to do something that would turn up a hard experimental fact or a hard observational fact. And so he found himself in 1919 on a ship, this very ship, in fact, sailing off to the south right after the end of the First World War with a team of scientists who were, as hopefully we all will be in just a few days' time, on their way to observe a solar eclipse. Why? What Eddington and his team were doing was testing a certain prediction that Einstein's theory made, that light would be bent by a gravitational field by a certain angle, a different angle than Newton's theory predicted. Or I should say, really, Newton's theory plus a whole lot of physics that had been done in the interim. So the idea was to actually, the expedition split into two, to go to two different places in the path of totality, to photograph the positions of stars, stars behind the sun at that time, and to compare those photographs to photographs of the very same stars when the sun was nowhere around. If the bending of light by the sun would create an effect where the stars, when the sun was around, would appear to be displaced outwards from the sun compared to the photo without. The whole thing would have been a lot easier to arrange if it were possible to photograph those stars without waiting for a solar eclipse. All you need is for something with a lot of mass, the sun to be sitting in front of your stars. But of course, the sun is not only very heavy, but also very bright. And so we need to obscure that brightness. Fortunately, we have the moon. But it does involve waiting and traveling to a very particular place. So that's what Eddington and co. did. Here's the setup in one of those locations, the one in northeastern Brazil, in Sobral. There's a couple of telescopes there. They couldn't take the telescope mountings with them, so the telescopes are just laid out flat, as you can see. And then in front of the telescopes, you should be able to make out a couple of mirrors that would actually be pointed at the sun. Here's one of the photos from that very experiment. What you see here is it's a negative, so this is the sun eclipsed. The big white disk is of the dark disk of the eclipsed sun. And off on the upper right-hand side, you can maybe see some faint lines. Those are pencil marks that to help the experimenters pick out the stars in question. Now, as I said, what they were looking for is movement in those little dots. In a photograph like this compared to a photograph of the same stars without the sun, taken in the middle of the night. What they were looking for was a difference in the positions of those stars of about 1/60th of a millimeter. Okay, that's about a quarter the size of the dot on the photographic plate. Okay, why am I telling you all of this? Apart from the eclipse theme, which seems appropriate. I want to distinguish two different ways of using observable facts or bringing observable facts into scientific theorizing. One of them is the Aristotelian way. Of course, here wave my hands and generalize a little bit. Aristotle was interested in explaining facts like the path of the moon through the sky, the fact there are rainbows, the fact that life is so well adapted to the environment, and he found a theory that made sense of those facts. That was the sense in which he wanted his theories to be, to accord with the observable facts. But what we see happening in something like the Eddington experiment, which is very much characteristic of modern science, is a little bit different. Here, the facts that are at great expense in time and money being fished up are not the big facts, or not only the big facts that we really want to explain and understand that make scientific knowledge so worthwhile, but little things that are really of no intrinsic interest at all. The movement of this little dot on a photographic plate. That's no fun, but that is the difference which will actually enable us to distinguish these two theories, Newton's theory and Einstein's theory, that are otherwise very similar in what they predict about what we'll see around us, about the movement of the planets and so on and so forth, even if they give very different explanatory stories ultimately about what's going on. Newton positing a force of gravity and Einstein positing no such force, and rather explaining what Newton attributes to the gravitational force to the actual curving of space-time. Okay, so what I've said so far is, in some ways, I hope, somewhat familiar, certainly not astonishing, that modern science spends a lot of time trying to distinguish theories which make similar predictions, but not exactly identical predictions, by doing experiments, often very fancy experiments that involve a lot of equipment and a lot of time. The only thing maybe you might be wondering at this point is, well, why didn't Aristotle think of that? I'm sure that Aristotle was as smart as Einstein, more or less. Why didn't that occur to him? I do want to get onto that question eventually. It's not what the question I'm going to address right now, though. Instead, I want to ask the question exactly how it is that modern science sets up this kind of competition to explain the little facts. And here I think I can say something that will be surprising, or I hope will be surprising to a lot of you. So I see modern science in contrast to all of the other sciences, Greek science, Chinese science, Indian science, and so on, as being animated by something that I call, in my book, this is just my term, the iron rule. I call it the iron rule of explanation. And you can get a sense for what this rule is, perhaps by starting with Brian Greene's point here. So I'm going to, and the iron rule you could see as a kind of generalization of this. So Greene is saying these aesthetic judgments don't arbitrate scientific discourse, only observable facts do. And the iron rule is taking that idea and that only observable facts count, and using it to exclude not just aesthetic judgments, but any kind of other judgment that ordinary human beings might take to be relevant to determining the truth about things. Aesthetic judgments figure, I think, very largely in modern theoretical physics, but at other times in the history of science, religious or theological concerns have been very important, especially in biology. So we find, but also in physics, we find thinkers in the 19th century, for example, like William Whewell or Lord Kelvin, were clearly very much moved, and they were willing to say so publicly, by their own religious beliefs in determining what was reasonable and what wasn't. Those kinds of concerns also ruled out by the iron rule. It's all got to be empirical. It's all got to be a matter of what your theories can predict or explain in the way of stuff that's measurable. So there's a prohibition here built into this iron rule on any kind of reasoning that is not empirical reasoning. And there's a little bit to say about what really counts as empirical reasoning or empirical testing, but I won't go into that. It's nothing that would really surprise you. It's about the very thing I've been talking about up until now, the ability to predict or explain or somehow derive the details of some phenomenon or other. Okay, well, I said I was going to tell you something that might be surprising here. Finally, here it comes. This prohibition, this iron rule, is, I think, not a stricture on scientific thought in general. In fact, it's not a stricture on scientific thought at all. It doesn't put any constraints whatsoever on the way scientists actually think about what theories are plausible, what theories are likely to be true. It is purely, one way I like to put it, it's purely a speech code. It's a prohibition on bringing up anything but empirical testing in a particular place, namely scientific journals. So the scientific journals are the official records of science. That's where you must publish your research if you're going to get credit for it. And in these journals, that is where, this is what Green, I think, is really talking about when he says aesthetic judgments don't arbitrate scientific discourse. Scientific discourse means the journals, and what Green is saying is that in the journals, it's all about the hard observable facts. So it's not as if these various physicists are somehow breaking the iron rule, trying to dodge the iron rule when they make these claims. I take these claims entirely at face value, and I believe that these different thinkers were genuinely moved by aesthetic judgments in just the way that they say. And that is, as far as the rule is concerned, is completely fine. In fact, it may very well be helpful in certain ways if it turns out that beauty really is a good guide to truth. But the thing is, when they go to put their theories into print and argue for them in print, they may not bring into the story any kind of argument that's not just about predicting the facts. And that's why Eddington, the great mathematical physicist, found himself supervising this purely empirical enterprise, an enterprise that really didn't require a whole lot of mathematical sophistication at all, but just sailing off and making very careful and precise measurements of the positions of certain little dots of light in the sky, because that was the only way he could, in the official channels of scientific communication, the place where scientific arguments are staged, the journals, the only way he could persuade people of the truth of Einstein's new theory. Okay. So we can see that iron rule in a way as setting up, I think of it, a kind of a game. And I call it a game because it's setting up a certain rule that scientists in their thinking don't necessarily follow. They know if they're going to publish in the journals, which they have to do if they're going to be scientists, they have to follow the rules. That's where they're playing the game. It's a game where the only legitimate moves are empirical moves. And there, in that game, a successful move is always going to be one that empirically discriminates between different theoretical possibilities. So this is the way the iron rule works, not by telling scientists that they must themselves become empiricists, but by putting them in a situation where they have to act like empiricists, where they have to act, sort of take on the role of empiricist. By empiricist, I mean somebody who's purely concerned with empirical reasoning. And in this way, it elicits precisely the facts that, as we can see, I think in the long term, have been so important to what I earlier called the progressive character of modern science. Okay. Yeah, I still haven't gotten to irrationality, notice. Is it okay to wait till the end of the talk to answer a question?
I don't want to disturb your, anyway,
Okay.
it's some observation, but it's okay.
Okay, all right, great. All right. So now I want to turn to a question about motivation in science and the importance of the iron rule in motivating scientists. So I'm going to talk just a little bit. Let me see. Well, I certainly have time for this. This is the island of Daphne Major. It's although in spite of the major in its name, it's actually only about half a mile across. It's one of the islands in the Galapagos, and to that island for many decades, these two biologists, Rosemary and Peter Grant, would go. And you may know a little bit of this from maybe Jonathan Weiner's book, The Beak of the Finch, where he writes about the Grant's research. Although that book came out a little too early to actually explain what is perhaps their greatest achievement. Anyway, they would go to this island. The island is populated by the famous Galapagos finches that Darwin wrote about. And they monitored the finch populations. Actually, they monitored not only the finch populations, but the lives of every particular finch on the island. So they were keeping track of the finches on a, as it were, a per finch level. They knew each one. And over a period of about 40 years, they went back every summer and tracked these individuals and to see what was going on with them. What they were interested in is whether as the conditions on the island changed from time to time, they could see natural selection at work. And they did see that. They saw something more interesting still, actually. They saw the creation of a new species by hybridization. This finch here. In 1981, when they'd been visiting the island for only 8 or 9 years, so rather a long time for that to be your summer break, they thought something interesting was going on, but it was actually only after about another 25 years or 30 years that they decided they really had enough evidence to go public with this. Actually, now I'm looking at the dates, even more than that. It was in 2018 that this discovery was announced. So that's quite a marathon, but a marathon with an extremely interesting outcome. Take these two scientists, Andrew Shalley and Roger Guillemin. Guillemin actually, like several people I have now mentioned in this talk, died very recently. Both of them working as rivals to try to discover the structure of a certain molecule that seemed to do something very important in the brain, a brain hormone that played an important role in certain signaling paths. Some work that has, like much of this other work I talk about, which has been written about very well by a couple of writers, and in the case of Guillemin's lab, actually also served as the home base for Bruno Latour's revolutionary work in the sociology of science. That's somewhat by the by. What I want to emphasize here is again, the relentless nature of the task. So Guillemin and Shelley were both trying to determine the structure of this molecule. The technologies they were using to determine the structure were nothing too special. In fact, they were using machines that you could just order from a scientific equipment company. What made this project so difficult was that the molecule only occurs in tiny proportions in the brain. So few that, in fact, by far the largest part of their experimental program, which went on for the best part of a decade, was simply collecting enough of the substance, TRH, to analyze it. And so this is Shelley talking about it. He had trucks heading down to his lab in New Orleans from the Oscar Mayer factory, full of pig's brains, truck after truck, and he sat there for year after year, simply extracting what he could get out of those brains, trying to build up a large enough sample to do the kinds of measurements that needed to be done to determine the structure. Here he is talking about just how difficult that work is, and here's Nicholas Wade in a great book he wrote about this, the rivalry between Shelley and Guillemin, describing the kind of thing that Shelley was doing every day, just essentially something that required a lot of skill and knowledge, but still was just a kind of after the first day, just this kind of day after day rote application of these methods to extract this substance, which in the end he succeeded in doing. In fact, Shelley and Guillemin ended up sharing a Nobel Prize, or at least half a Nobel Prize, for discovering the structure of this molecule. Okay, why am I telling you all this? What these two examples, and also the example of Eddington, I think, bring out is some further characteristics of those little facts that discriminate between theories in science, or so often the facts that are crucial to discriminating between theories in modern science. These facts often involve very small details or very close observation. Think of the Grants every summer tracking their finches. or recording, investigating very complex structures. This work is crucially really time-consuming, really expensive, and actually also, as Shelley was saying, really tedious. Okay, I mean, it's wonderful to be able to sit here as the consumers of this science, and you can get 5 or 6 really fascinating discoveries in the course of an hour, but each of those discoveries can represent a decade of work or 4 decades of work. Put yourself in the lab coat rather than the beneficiary, and you can begin to see just how, in many ways, what hard work it is and kind of boring work it is often to be a scientist. Of course, it's fun too sometimes. But still, it's also risky. Things can go wrong. So here are just to give you some examples. You can you sail all the way to an island off the coast of Africa, as Eddington did. He was not in that Brazilian location, but in the other one, Principe. And then it turns out on the day of the eclipse, clouds. This is what happened to him. And then he records in his journal, about 10 minutes after the eclipse was over, the skies cleared up. Yeah, that doesn't happen to us. Or you go to the island for decade after decade, and nothing that interesting happens. You know, you gave it a shot. Or in a rather different kind of risk, when Guillemin and Shelley were competing to discover the structure of the molecule, if one of them had been first, the other one really wouldn't have gotten any credit for it. Well, maybe some credit for incidental discoveries along the way, but it would have been one of them walking away with the Nobel Prize and the other one with just, I guess, a big pile of pig's brains. So you might wonder, how is it that scientists with certainly no certain prospect of their long, hard work turning into a really valuable discovery, how is it that they kind of find the will to turn up in the lab or go to the island or whatever it is every day? What is it that, no doubt there are some kinds of people out there who are just perfectly calibrated to be this kind of scientist, but a rather small minority. I think modern science needs rather more people than just those very special individuals if it's going to succeed. It has to be able to take very talented, but otherwise ordinary humans, and turn them into people who are willing to do this kind of work day after day, week after week, year after year even. How's that done? Well, a part of the explanation, I think, is, again, the iron rule. And here I'm just going to say exactly the same things about it that I said before, but now with an emphasis on this motivational question. The iron rule sets up a kind of a game. If you're going to do science, you can't be Aristotle anymore. You can't think that, well, you can think that way. You can't argue that way. You have to play the game. In the game, that means making empirical moves. It means finding some kind of little difference that's going to distinguish your theories. And then, it's not enough just to find it. You have to, or at least somebody has to. You know, Einstein was lucky to have Eddington, of course. And theoretical physicists in general are lucky enough to have the many, many thousands of experimentalists who actually spend all the time and money on making this happen. But somebody has to actually go out and do the experiments. But that's the only way to do science. So scientists, if you like, if they want to be scientists at all, have no choice but to do these things. That, I think, is a really big and important part of the motivation story. All right, then. Now, irrationality. Let's go back to the beauty stuff again, just one more time. Here are some very eminent scientists testifying to the importance of aesthetic judgments in their own thinking about what theories are promising and what theories are not. As Brian Greene remarks, those judgments have to be put aside entirely when they come to try to convince their colleagues of the virtues of their ideas. Okay. So far I'm just repeating what I said earlier. But there's something very weird about this, something actually I think, at least, I mean, I suppose for many years as a philosopher of science, this never occurred to me, and now it's occurred to me. I can't get it out of my head. It's that kind of thing. On the one hand, we're being told, quite sincerely, that beauty is incredibly important as a guide to truth. On the other hand, we're joining in an enterprise where the official rules of the enterprise say you may not pay any attention to beauty at all in your writing. Okay, so you're joining in this game, but it's not just a game. It's also the in the scientific journals the primary and only official channel for you to communicate with the rest of the world about the importance of your ideas. You're joining into this, willingly subjecting yourself to this speech code, this rule that says ignore what you yourself believe to be a really important and certainly available, a lot easier to recognize the beauty of a theory than to do those experiments. To ignore a source of information that's at your fingertips and that you think is really important to doing precisely what is supposed to be being done by science and by scientific argument, finding the truth. And this stricture, so I'm zeroing in here on the rules of scientific argument, the rules that govern what goes on in the journals, violates what philosophers sometimes call the principle of total evidence, but which should sound like a quite unremarkable maxim of rationality. If you care about getting something right, if you care about being successful in some enterprise, then take everything into account that is relevant, or at least, unless it's just too complicated or expensive. There's nothing complicated or expensive about taking beauty into account for someone like Eddington or Steven Weinberg. So if we are to follow the principle of total evidence, we absolutely should be bringing in everything we think is important and relevant to our reasoning, our public reasoning in science, including aesthetic judgments where they're appropriate. But the iron rule says no. And it's in that no of the iron rule that I see the irrationality of science. I shouldn't say the irrationality of science as a pursuit, because I think that science is, go back to my title, highly effective. There's nothing irrational about doing science, and I don't think scientists themselves are being irrational by doing science. And as I was saying earlier, scientists are in fact fully able in their own thinking to take into account everything they think is important and relevant. It's rather the rules of scientific argument that are irrational because they violate the principle of total evidence. And yet, it's precisely this narrowness. It's precisely the fact that the game is set up so that only empirical arguments count that explains, I think, the success of modern science. That's what focuses scientists on these small or otherwise very hard to obtain facts, and that's what pushes them to do whatever it takes, even if it's decades of work with no guarantee of success, whatever it takes to actually bring those facts to the table and to bring them to bear. So science, I think, is highly effective in at least a big part of the explanation for its effectiveness is that these rules of scientific argument, the iron rule in particular, is irrationally narrow, which means that, if correct, no, nearly there, if I'm correct, that to actually, if you like, stumble across the secret to doing modern science, human beings had to realize that doing something irrationally narrow would actually work really well. So, to return to an earlier question, if you want to know why Aristotle didn't follow the iron rule, the reason is it would have made absolutely no sense to him whatsoever to dismiss all of the philosophical considerations, for that matter, the aesthetic considerations that he saw, or certainly fervently believed were so important to figuring out how the universe worked. And likewise, for all those other thinkers, there's just something very, very unpromising about the iron rule. As a matter of fact, it turned out to be amazingly successful. All right, well, thank you very much for listening. That's my book. That's where I tell the story in greater detail.